effective invertible arbitrary image rescaling. Most image super resolution models are optimized for upscaling only. Some new bidirectional models aim to improve it by optimizing downscaling and upscaling jointly, but they are limited to fixed scales mostly, and the bidirectional model that is capable of rescaling of arbitrary scales is underexplored. There are two existing studies before ours. One is our own work, BELET, that's the first one for this challenging task. And there's another one by Xin et al. Using encoder-decoder alternative model for the same task. Our model is based on the original invertible rescaling network IARN, but the key innovations include changing the hard transformation with a channel splitting. So the main transformation is conducted in original resolution. And at the end, there's additional downscaling and upscaling to get the output of the right resolution. To make this model working effectively, we need YH to be rescale invertible. That means after rescaling, YH equal to YH hat. This is the detailed network architecture showing the key innovations of our method, including preemptive channel splitting at the beginning and the scale encoding added at both directions and both branches. Lastly, the dense convolution is used to upgrade the original invertible block. As shown from the ablation study, all the innovations are useful in improving the results, but the most important is the preemptive channel splitting, as it is critical to make our network effective in invertible rescaling. Quantitatively, for different datasets, our IARN is the best overall, and also continuously over the scale between 1 and 4, our model is leading everybody else, including the concurrent AIDN, as in the magnified view that show the difference. Ours is the green versus the orange of AIDN. And these are the visual examples to show our higher performance. Additionally, these models are also learned to generate low resolution results. So it's important to get high visual quality with those. And our model is the best quantitatively, as shown in the tables there. And also visually, in the worst case of DIV2K, our result is the one with the least amount of false color artifacts. Lastly, our model is capable of achieving asymmetric rescaling. That means the scaling factor along the horizontal and vertical are different. This is done without any change in the model or network architecture, as our scale encoding is designed with that considered. Thanks a lot for your attention. This is the end.